Good morning, everyone. I'm sorry I couldn't get a copy for you today. Right. So the paper I'm presenting today is called Learning Visual Question Answering by Bootstrapping Hard Attention. So the reason why I chose this paper is that over the past few weeks we have been talking a lot about attention, right? So why are we talking about attention again? So this graph is just a chart that shows over the course of the past few years how many papers that have been published in artificial intelligence and image processing have talked about attention in the abstract or in the title. So as you can see, there's a huge spike in the recent years. So it's obviously some topic that's of interest to researchers, right? So that's why we're talking about it again.
So this is your own chart?
No, so it's from some online source.
Slow down.
I'm sorry? It's exported. There's some citations below.
Yeah, okay.
First quarter of 2019.
Yeah, so the 2019 one is not fully updated yet. Yeah. If you're interested, I can send the link after the talk. Okay, so what's the importance of attention? Why do we need attention? So there's a very classical experiment on attention that I would like to share. So in this video, right, what you're supposed to do is to count the number of times the ball is being passed. But in the background, actually, there's something interesting going on. So I won't spoil what's the interesting thing, but let's just try this. Okay, so how many passes do you count? 13. Any other answers? Okay, so the correct answer is actually 15. Okay, so just to prove I'm not lying to you, alright? Okay, but the point was that when you look at a video, right, when you have something interesting in the background, you might actually forget about the task and you look at something else. Okay, so this is why we are talking about attention and why we are talking about hard attention. We want to ignore the background. Okay, so let's rewind a bit. Let's talk about how people have been implementing attention. So this is a very typical way to do attention. So what they do is they have some sort of convolutional input, and then they take some context vector or matrix, they multiply it to get some attention feature map, and then they combine the two inputs into a new input. And then they can do it for different layers. So this is at the convolutional layer, they add in another different attention matrix. So this is one way to do soft attention. And a more recent way to do it is from this paper called Attention is All You Need. So this is part of the transformer model. So what they do is with input X, they take 3 weight matrices to give 3 vectors for each input. So the query, the key, and the value. So what they then do is that they take the product of the query for the input word multiplied by the key of all the other words to give some score. Once they have the score, they do a softmax, and then the softmax is going to give you the attention distribution across all the words. So they take the score, the attention, they multiply it by the value to give you this softmax multiplied by value vectors, and then they sum it all up to give you the output for this input. So it's called self-attention because you're actually attending to both yourself and all the other pieces in the input. So now we come to hard attention. Why is hard attention important? Because it's actually very hard to train soft attention. So the BERT, which is a pretty famous model for language modeling, right? They take 4 days to train in 16 cloud TPUs. And recently there's been a newer model by OpenAI that's called GPT-2. So it's an order of magnitude larger than the original GPT, which is about the same size as BERT. So this shows that the soft attention, right, in order to train it and to get state-of-the-art results, you actually need to use a lot of computational power. You need to train a lot of stuff. Okay, so the benefits of actually using hard attention is that you only need to process the information that you think is relevant. So in the traditional setting, right, if you have a question and you have an input image, what you have to do is you have to calculate the output for the entire image, and then you have to combine that representation with the question to get your answer. But for hard attention, what you do is that you actually only select the important parts of the image and you calculate the answer based on that. So this actually saves quite a bit of computational power. So in the experiments later I'll present, they actually cut it down to up to like 32% of the input image. So they discard the rest. Right. Okay, so the traditional difficulty of training hard attention is that you actually, so most algorithms, they rely on backpropagation to calculate the gradients for updating the weights, right? So in hard attention, because you choose which cells you are looking at, which points you're looking at, so it's actually a discrete choice, and the process is non-differentiable. So you actually can't actually calculate the gradients for the parts that you don't look at. So that's actually one difficulty of training hard attention. Okay, so for this model that we're talking about today, what they did is they actually only backpropagate the weights through the activated neurons. But the activated neurons are updating the weights of CNN and one-by-one convolutional network, or MLP. So they're actually using the same set of weights here across the entire image. So the authors argue that this actually doesn't affect the training much. So you still can actually train well with a subset of inputs. Okay, so the architecture of the hard attention network, which is the name of this model, is that you actually have a CNN that acts on the image. You have a question that you take the embedding and LSTM to get a representation of the question. You broadcast it onto the CNN. So this single representation of the question is being concatenated with all the outputs of the CNN. After that, you do some selection of which inputs you want to take in, and then you use another network to aggregate all the features, and then you classify it. Okay, so first we actually zoom into the attention mechanism. So how do they actually select all these, select which inputs do they want to attend to? Alright, so quick refresher of the traditional soft attention formulation. So you have your X, which is your image, you take the CNN. The Q is the LSTM representation of the question. So you calculate some weights based on some model, and this is actually your attention distribution. So then you multiply these weights by your X, the input, to get the hidden representation. So the hidden representation is actually just the weighted version of the Xij. Alright. Okay. So for hard attention, like I said before, they take the same LSTM output of the image and the same CNN output of the image, same LSTM output of the question, and then they run a different neural network on it. So for the image, what they do is a one-by-one convolutional network. So it just looks at each input in sequence. And for the question, it's a multilayer perceptron. After that, what they do is that they sum up the values. So they broadcast it to the same dimension D, and then they sum all of the X and Q up. So this is to combine the representation of the image with the representation of the word, the query in question. So X is the image, Q is the question, you add them together. Right? So it gives you this MIJ. From the MIJ, we take the L2 norm, and we say that that is actually our probability of selecting each of the MIJs. Okay. So once you have the probabilities, you can actually select the ones that you want to keep. So there's actually two ways of doing it in the paper. So one is the original hard attention network. So they just select top K entries. So given this entire array of P's, right, I just select the top K number of P's, and that forms my M hat K. For the other way to do it, it's called adaptive hard attention network. So what they do is, after they take the P, right, they softmax it, and then they say that this value must be greater than tau for it to be selected. So this tau is fixed, but the probabilities can change. So as the probabilities change, more or less of the neurons can be greater than the tau. And the authors say that the tau can actually be set to any arbitrary value, but one value that they used was this 1 divided by the width multiplied by the height of the image. So the intuition is that you want so assume that you have an image that's uniformly interesting. So every single part is going to be important. Then this tau value is going to be even, right? So it's going to be the same importance for all the different points of the image. Okay. So that's what the author said. If you are greater than this tau in that point, that means the probability of this part of the image being interesting is higher than some other part. So if you increase the level of PLI in this area, then the other side must decrease. So that side is going to fall. So this is one interesting tau that they used. Okay, so moving on. Alright, so that's how they select the tension. You're too early, half an hour. Alright, so that's how they actually select which inputs to attend to. So now we talk about a bit about how they actually sum up all these inputs, because the sizes can be different, right? Especially if you have the adaptive hard attention network. So how do they actually join all these features into the same sized output? So the feature pooling is done very simply. If you have soft attention, one way to do it is you just do sum pooling. So you just add up across all the dimensions, just sum all the values up. Okay, so similarly, if you have hard attention, you just sum up all the m's for 1 to k. Okay, so the authors also used a different pooling mechanism. It's called the non-local pairwise operator. So it sounds impressive, but actually when you look at the formula, right, it's the same as the transformer. So what they do is they have the query, they have the key, multiply together, softmax it, multiply by the value. So it's essentially it's similar to what the transformers use. They just give it a fancy name. Okay, so the authors actually conducted a few different experiments to try and show how effective the hard attention network is. So for this experiment, what they do is they're comparing the hard attention network, so the non-adaptive one, the one that you have to select K, and then they compare the different types of pooling. So sum is the sum pooling, pairwise is the transformer style pooling, and then the K is over here. So they actually go from 16 all the way to 100. So from the results, what we can see is that it's there's this one that's pretty interesting. So for the hard attention network, pairwise, right? If you only select 48% of the neurons, you actually get a higher overall result on the test set as compared to 100%. So this, the author's explanation is that some of the background can actually confuse the model, especially when you have a very difficult task, like it's 50-50. So by looking at less of the image, actually improve the performance a little bit. And the hard attention actually outperforms the soft attention networks. Yeah. So
what is the evaluation matrix?
Evaluation matrix.
The number of years.
I think it's accuracy.
Or t-test or something.
T-test?
Or any other sequence.
No, they didn't provide. It's a poster, come on. Alright, so moving on. Now they compare the hard attention network to adaptive hard attention network. So you can see that the adaptive hard attention network actually is worse performing as compared to the hard attention network. But what is interesting is that for the overall scores, right, the adaptive hard attention network actually requires significantly less neurons, the percentage of the cells, as compared to the hard attention for the same level of performance. So this is 27.4, 27.43, but the difference in the percentage of cells activated is about 7%, 6%. So sort of like suggests that the model is able to learn like which neurons are actually the more important ones. So you can actually discard like almost 6% of the neurons without affecting the overall score much. So similarly for the pairwise one, same level of activation, you get about 1% increase. And if it's to get to the same level of performance, you actually need to use 48% of the hard attention. Okay. So this last one, it's about for the questions, right? They actually have a multi-layer perceptron. So they vary the number of layers in the multi-layer perceptron from 0 to 2. And we can see that actually by increasing the number of layers, you actually get slightly better performance as compared to the same percentage of cells activated. Okay. So now the authors actually compare their model to standard. Oh wait, no. So this part is just the qualitative analysis first. So they compare adaptive AdaHAN to the hard attention network, and the highlighted regions are the regions that are actually activated. So it's a bit hard to see, but you can refer to the paper if you have it on your machines. Okay, so the left is the adaptive model, and then the right is the original hard attention. And you can see that actually the models perform pretty similarly. Adaptive one doesn't seem to understand, so this question is what color is the skirt, right? The adaptive model is actually looking at someone else. It's not of the tennis player, it's looking at the boy or ball girl. But it still gets the correct answer, so quite okay. Okay, moving on. This one is additional qualitative analysis for the adaptive hard attention network. So they were just trying to show that there's a lot of information that you don't need in the image when you actually want to answer a question. So like how high is the man jumping? You actually just need to look at this part to tell like it's about 3 feet. Alright. Okay, so this part is the one where they actually compare the model to other implementations, other models, right, to see how good or how bad the AdaHAN does. So they actually use a standard dataset, the CLEVR Dataset. So CLEVR Dataset, it's a synthetic dataset. They actually have a few tasks within the dataset. So the questions are something like, is there an equal number of large things and metal spheres? So your model should be able to differentiate like what are large things, what are metal spheres, and count them. So it's quite a challenging dataset. So for the performance, the AdaHAN results are below. The pluses indicate actually the size of the model. So they actually scaled up what we were discussing, the hard attention network. They scaled the input size up to match the one of the review model. Yeah, so we'll talk about that later. But they actually scale up the inputs to actually make the models more comparable. And you can see that actually it outperforms a lot of other models. So stuff like soft attention, CNN, LSTM, all over here. And one thing that they noted was that for the hard attention network with the sum pooling, the comparing of numbers actually performs a lot worse than the other models. So it's 88%. So they mentioned it, and I think it might be interesting to look into why, but they didn't explain more. Yeah. Okay, so that's the end of my presentation. If you have any questions?
Can you go to the table again? They say hard attention and the adaptive one. And saying it uses fewer pixels, right?
Yes.
So this one I don't really get it. So the hard attention is based on the top K, right?
Yes.
And the adaptive one is based on the threshold.
Yes.
So then doesn't it just depend on what is the K, what is the threshold? Why can we claim that one is going to use fewer one than another one?
So this one is just a calculation of, at the end of the training,
Right.
they look at how many neurons are activated, how many inputs are
Yeah,
activated.
but you set the threshold.
Yes, you set the threshold, but they
So-
fix it for all the experiments in this paper to this
Right.
same.
But how do you define equivalence between the tau and the K?
They don't.
So they don't. So then how can we claim that later on the smaller number is because of the model, not because of the tau or the K?
But the smaller number is a function of. So this one is fixed, right? They select the 32% and as the K.
It's 32% as
So you
the
calculate the
K.
width by height, and then they calculate what's 32% of that, and that's your K.
So the K here is a percentage of that
Yes.
thing. So that means, and then what's the claim here?
The claim here is just that by using the adaptive method, you get similar performance with less cells activated.
But we don't know what is the performance when the K is 25%.
For this,
Yeah.
they don't show the results. They show the results for the pairwise one, the 32 and 32.6.
32. Okay.
What they're saying is that they should have taken these numbers and run the top K with these.
So that's what I was wondering. Because what is the equivalence? Isn't it just a matter of threshold of the top K?
I don't think they were trying to analyze like the relationship between the K and tau. They were just trying to make a statement that
But what is the meaning of adaptive then?
that you are not actually limiting the number of indices that you select. It's just changes based on how many P's are above the threshold.
But the defining a threshold is like defining a K.
Yes.
Okay, alright.
It's not necessary.
That means if I know what is the threshold, then eventually is anything above the threshold is a top K. For that
If
threshold.
all uniform, then nothing will be selected, right?
If it's uniformly important.
Hmm?
If it's uniformly
It's uniformly
interesting.
Important, still nothing will be selected.
So-
if, at least one is a little bit more interesting, then one will be selected for attention.
And what is the tau value?
So they fix it as 1 divided by W times H. So the W is the image width, the H is the image height.
1 over W times H. So this is basically uniform.
Yes.
Anything that is more than uniform is selected.
So for the top K here,
Yes.
do they use the weights or they all have the same weight?
For the top K, they just select the top. Okay, so for the benefit of the list, you have CNN output of the image, right? And the RSTM output of the question. Okay, what you do is you run again the CNN one by one on the CNN output. You run the multilayer perceptron on the question. So you combine these two representations into this M, and then you just select the top K M's where the L2 norms are the largest. So in the hard attention case, it's fixed, just top Ks.
And the K here is how many again?
So they
So they said 38. 32 or basically 1/3 of half, right?
Quarter, third.
So how does it reduce the computation compared to the sum attention?
So that's the interesting thing. In the paper, they actually said that they created a TensorFlow estimator
Reduce what?
computation.
The claim is do less.
They claim that you need less to run it, right? But I think in the paper they say that
Because the expensive part is the part that you calculate the weights.
it's yeah.
But here you also have to calculate all the weights and then you rank, right? Like compare.
The claim is that you reduce the number of trainable parameters.
How so?
It's the same, right?
Not many,
Yeah.
not many
Because you, instead of having to learn the weights for all the pixels in the weights array, you only need
So
to have the weights for the selected pixels.
But how do you know which one to select?
So I think the speed up comes from the
Yeah.
aggregation part. So when you do this part, if you do this non-local pairwise, right?
Okay.
Yeah. Instead of having to do it for all the inputs, you only do it across like the 16 or 32 of the
Okay.
piece of inputs.
Okay, I'm gonna stop the questions there. Ask the questions later.